Okay, so algebra, we're going to be looking at a lot of ways of manipulating equations and things like that. Right, so some basic expansions and, well, basic formula you need to know. So x plus y squared, you can expand it like this. So if you had this, you could factorize it as x plus y squared. Similarly, x minus y squared, and then you can have the cubes. So x plus y cubed, x minus y cubed. These are the formulae here. These can be generalized, well, at least the addition one, so you can generalize it like this using the binomial expansion, right? We would have seen this in the combinatorics section before, where n choose k is given by this formula. Also, like I said, if you're not comfortable yet remembering this, you can figure out what n choose k is using the Pascal's triangle. So the binomial expansion, so you can write it like that, or you can use the summation notation. And if you wanted x minus y to the power of n, you just replace y with minus y, right? And then you'd have a minus 1 to the power of k times y to the power of k. All right, so that's sums, and basically that's when you have powers of sums or differences. So now we have sum and difference of powers, which is slightly different. So now we have, like, for example, difference of squares, difference of cubes. You can have difference of nth powers, right? And then you can factorize that like this, actually. So you can think of this as x minus y times x plus y, x minus y times this, and then so on. As long as you have x to the power of n minus y to the power of n, you can always factorize that as x minus y times something, right? You don't have to learn it off. You could actually try to figure out as you go. You know x minus y is a factor. So for the first term here must be something to multiply by x to get x to the power of n. And that something has to be x to the power of n minus 1, right? Because n minus 1 plus 1 will give you n. And then if you have x to the power of n minus 1, you multiply that by this, you get minus y times x to the minus 1. You have to get rid of that, so you have to add something. So I'll add y by x to the n minus 2, so that when I multiply this by that, I'll get the same term as this. So except I have a plus now, so it cancels. And then you keep going like that. Right, so you could actually try to figure out this. You don't have to learn this off. You could figure it out based on what the expansion is. So simple one is this, x cubed minus y cubed. So x minus y, you have minus y by x squared when you multiply this out. Right, but actually, first of all, if you have x minus y, you need an x squared to multiply by x to get x cubed. But then if you have an x squared, when you multiply by minus y, you get minus y by x squared. So I need to add xy so that I could multiply this by x and get y by x squared to cancel with this new term. But then when I do that, I have xy times minus y will be minus y squared x. So now I need to have plus y squared to cancel that term when I multiply it. And you can check that when you expand this, you get back the original thing. All right, again, summation formula, you could use that there. Now that's with difference. With sums, it only works if the power is odd. So for example, you can't factorize x squared plus y squared, or x to the power 4 plus y to the power 4. All right, actually, I shouldn't say you can't. You could factorize those things, but you can't factorize it with integer coefficients. The coefficients would work out to be things with square roots, which yes, you could do, and yes, it's important you know how to do that, but not right, not for these things. All right, so yeah, so if n is odd, then you can factorize it using this, and again, you could try to figure this out. You don't have to learn it off. You could figure it out knowing that x plus y is a factor. Okay, so again, summation notation here. All right, so this is an exercise to factorize those things. Some more manipulations. So knowing how to combine things like this where you have the powers, this helps you. So for example, if I know a plus b is 1, and I know a squared plus b squared is 3, I need to find a to the power 4 plus b to the power 4. Well, using these two pieces of information, I can figure out what a, b has to be. right? Because if I square this, a plus b squared, I'll get the a squared and the b squared, and I'll get plus 2ab. I know what a plus b is. I know what a squared plus b squared is, so I can figure out what ab is. So we could do that, and we get ab has to be minus 1. And now, notice if I square this, I'll get a to the power 4 plus b to the power 4 plus 2a squared b squared, right? But I've already found what ab is, so I can substitute for this, substitute for ab, and get my answer. So when I square that, I get this, and I make a to the power 4 plus b to the power 4 the subject to the formula, and then substitute for the information that I have. So I get my answer there. This is a very useful technique for some algebra problems, being able to manipulate things. So there are different things you could do, right? For example, if I wanted to find a cube plus b cube, I could multiply this by this, and I'll get a cube, b cube, and some other terms. And you can do various things like that. If I wanted to get a to the power 6 plus b to the power 6, I could take this and cube it, right? Because that'll give me a to the power 6 and b to the power 6 plus some other terms, which I can figure out. Now, if I wanted a to the power of 8 plus b to the power 8, then once I find this, I could square that. Or you could even raise this to the 4th power, but that there's a lot of things to figure out. It's better if you square this. If I wanted a to the power 5 plus b to the power 5, then there are several different ways I could do it. I could find this and then multiply this by that to give me a to the power 5 plus b to the power 5. Or I could square this and then multiply that by this. Or I could figure out what a cube plus b cube is and multiply by this, right? There are different combinations you could use to get the right powers. And some questions, what you actually have to do is use combinations of the different products to actually give you what you want. Okay, so given that x plus 1 over x is equal to 3, find x squared plus 1 over x squared. Now, the nice thing about this is when you square x plus 1 over x times 1 over x gives you 1, right? So there's no x in that, so it's nice, easy to work with. So squaring that, I get this squared is x squared plus 1 over x squared plus 2 times x times 1 over x is just 2. So automatically from this, I can figure out what x squared plus 1 over x squared is, right? Make that the substitute formula. So it'll be this minus 2. And I know what x plus 1 over x is, so I get the answer. Right, so these are questions you can try. So I gave you x plus y and I gave you xy. I need to figure these out. This is just a straightforward manipulation. And then this is similar to the second example. Right, this example here. This one is slightly different, but it's the same idea. So I want to see what you'll do for that. All right, simultaneous equations. So with simultaneous equations, what happened there? Yeah, with simultaneous equations, the ones that you all will be most familiar with at this stage is where you have, for example, a system of 2 simultaneous equations and 2 variables, or maybe 3 equations and 3 variables like this, where you can make one variable the subject of the formula and substitute into another equation, and you do that as many times as you need. That only works if it's a simple linear equation like this, right? So for this example, yes, it would work. It would take some time, but it would work. But for more complicated ones, when you have like x squared and y squared or xy and things like that, that is not going to work so nicely. So you have to try to figure out how to manipulate the equations in other ways to simplify it and get what you want. So with this one, notice it's kind of symmetric, right? So I have 2x, y, z, I have x, 2y, z, x, y, and 2z. If I add all of these equations, I'm going to add 2x and x and x. That gives me 4x. I'll have 4y and 4z, right? So I can figure out what x plus y plus z is. Now compare this with this. The only thing that's different on the left-hand side between this and this is that this has one more x term. So if I subtract this from this, I'll actually be able to figure out what x is. Right? And automatically I'll get that x has to be 0, and then you can do the same thing for the other equations and find y and z. So this technique here, this is much simpler than if you had to go and say, Okay, so make z the substitutive formula here, make z the substitutive formula here, and then equate those or something, and then substitute. You trying to do things like that is very complicated for this. All right, this is another one. So consider this example. Now this has x squared and y squared and xy. So if you try to make x the substitutive formula or even y, you're gonna have to take square root somewhere, and that is not gonna be nice. All right. So what can you do here? Well, so it says here, adding equations to give it together gives you this, right? Which you can factorize easily like this. So if I add them, I'll get, basically, I'll get what I have here. So I have x minus 2y squared is 4. So basically x minus 2y is plus or minus 2. Now, another thing you could have done, right, is notice I have 2xy and 2xy. So if I subtract, if I say 4y squared minus x squared, this will cancel, will be 12. Right, that's another way you could do it. So you basically get 2y minus x by 2y plus x is 12, and then you could probably, well, if you knew that x and y had to be integers, then that would work. But because in this case it just says solve, it means we're looking at real numbers. So because of that, you can't say, well, okay, if 2y minus x by 2y plus x is 12, then I could take cases. You can't take cases because it's not integers, it's real numbers. So it doesn't have to be integer factors of 12, right? So be careful with that. In this case, the only way to do it is to add them. If you add them, you get this, right? Yeah, so you know x minus y is plus or minus 2, so you can take cases from here. Right, the left-hand side of the first equation, actually either equation, you could actually factorize this one or this one, and in both cases you get x minus 2y, or what do you get here? You get, yeah, you would get x minus 2y coming out somewhere. So from the first equation, you'll get, you know, x minus 2y is plus or minus 2, right? So you could take cases. If x minus 2y is 2, then basically x is minus 2. If x minus 2y is minus 2, then x would have to be 2, right? And then you could substitute. So if x minus 2y is 2 and x is minus 2, you could figure out what y is, similarly down here. And these are your two answers. Right. Usually with simultaneous equations in Olympiad problems, there's some clever trick you have to do to manipulate the equations. So if you see things with products and I don't know, anything where you could expand or try to substitute, and if you do that and it makes it more complicated, then don't do it, because there's probably a nicer way to do it. And the fact that you're making it more complicated probably means that you can't actually solve it like that. So always try to figure out whether if you add them, or if you maybe take 2 times 1 plus another times plus something times another to eliminate variables, then that would help. So like I said, if I had subtracted here, yes, the 2xy would go away, but it doesn't actually help me solve it. In this case, you actually need to add them and then factorize. Right, so these are some more examples here. Again, this you could solve this similar to the first equation, right? It looks kind of similar-ish. This one you could solve similar to the first equation. Well, actually it's more like the second, but still. So the different ways you could do this, right? You could actually add it and factorize it, this one. But you could also notice that if the product of these two things is 64, it means that none of them is 0. The product of these two things is 36, none of them is 0. So you can actually divide both equations, and you'll get a over b is this 36 over 64. So basically what you could do is get a in terms of b, then substitute back, get quadratic, and you could solve that if you wanted to. But like I said, you could also add and factorize. So this one here is not adding, right? This one you're going to multiply them, because if you multiply them, you're going to get x squared, y squared, z squared. And then you could figure out what x, y, z is and then divide. This one, all right, so this looks all complicated. So there's a xy here, but there's no xy anywhere else. There's nothing with z times x or z times y. So adding all of these 3 equations is not going to help. You're going to have to try to find a way to manipulate these 3 equations. what I would suggest is focus on the first two equations first. So from this one, you know z squared is xy, right? So if I take this 2z across on this side and square the whole equation, I'll get 4z squared, and I can substitute for z squared and get an equation in x and y alone. That might help. So try doing something like that. Okay, so inequalities, this is important. A lot of question, in the IMO, it's very rare nowadays to get like a full inequality question, a question where you have to prove an inequality. But there are a lot of questions where you can use you can either kind of introduce inequalities and use them to get a nicer solution, right? So one example is where you use inequalities to bound things, to get an upper bound or a lower bound for the answers, and then try to figure out the cases based on that. Another thing you can do is, without loss of generality, if things are symmetric, you can assume that x is greater than or equal to y and things like that. And that lets you do things with the, or make the conditions nicer. So it's important you understand how inequalities work. Right, so these are some theorems, these are some properties that you need to know. So if you have two positive things and you add them, you get something positive. If you multiply them, it's also positive. If they both negative and you add them, they're still negative. But if you multiply them, it becomes positive. Right, so if x is positive, y is negative, then x minus y is positive, right? Because minus y will be positive. Right, and also if you multiply them, or if you multiply a positive and a negative, you get a negative. If x is less than y, then minus x is more than minus y. When you multiply by -1, the inequality sign changes. Right, and this is the transitivity property that you would have seen something similar to before. So if x is less than y and y is less than z, then it means x is less than z. Right, and if x is less than y, then you can add something to both sides. So x plus z is less than y plus z. And you can also subtract from both sides. So x minus z is less than y minus z. If x is less than y and z is something positive, then when you multiply both sides, the inequality sign stays the same. So xz is less than yz if z is positive. If z is negative, the sign changes. Right? And if x is less than y and z is less than w, you can multiply across both sides. So xz is less than yw. Oh, that's assuming they're positive, right? But if x is less than y and z is less than w, you can add. So x plus z is less than y plus w. And like I said, if they're positive, then you can multiply. You have to be careful when one is negative because the signs can be messed up. Actually, when you make simple mistakes like things like this, like not checking to see things are positive or not, sometimes what happens, I've seen this happen already. People end up, for example, if you want to prove A is more than B, some people end up proving A is less than B. And you can't figure out why the sign is not the correct way, right? That has happened to plenty of people when they're working on problems in training. And the reason for it is because you didn't pay attention to some of the properties where some things maybe were negative, or maybe used an inequality that was actually the reverse way and you didn't realize. Right, if x is more than 1, then x squared is more than x. If it's between 0 and 1, then x squared is less than x. And if it's less than 0, again, x squared is more than x because this is positive and this is negative. Right, all of these things are strict inequality signs, but you could use, they all apply if you introduce the equal to as well. So if any of these you put in greater than or equal to, less than or equal to, it still holds. Be careful with these, right? If x is less than y, it does not imply 1 over x is more than 1 over y. So, you know, normally if things are positive and you take the reciprocal, the sign changes, right? For example, 2 is less than 3, but a half is more than a third. That is true, but when things are negative, it isn't necessarily true because, like I said, if you take, we know -2 is less than 3, right? -2 and 3. But if you take the reciprocal, minus a half is not more than a third. The sign doesn't change. And that's because you have negative and positive things involved. So these only work if the signs are the same. So Actually, they only work if everything is positive. So if x and y are positive and x is less than y, then yes, this is true. But if x is negative, it isn't true. Also, if x is 0, it isn't true. And this one here, if x is less than y and they're positive, then yes, x squared is less than y squared. But again, if x was negative, for example, x is negative 3 and y is 2, then 9 is not less than 4. So you have to be careful there. And in fact, if they're both negative, for example, negative 3 is less than negative 2, then the sign would change completely. But if one is negative and one is positive, then that completely messes things up. You have to be careful with that. All right, be careful with arguments like this. I've seen this plenty of times. Like you might go along in the proof, and in one line you prove x is greater than y, and then later on you prove x is greater than z. And because you prove x is greater than y before you prove x is greater than z, I don't know if it's a sort of like a mental thing, but it's happened to me before as well, where your brain kind of tells you, okay, you know x is more than y, and then you know y is more x is more than z. You kind of assume that means y is more than z, but it's not true. So you have to be careful with that. Okay, so this is a simple inequality, right? This is always true. X squared is greater than or equal to 0 for every real number x. It might seem basic, but this is actually very useful. And you could expand it. If you take x squared and y squared and you add them, that's still greater than or equal to 0. And then you can keep going. Note this is only equal to 0 and both x and y are 0. And if you have a sum of any number of terms, right, x1 to xn, and sum of those things squared, that must always be greater than or equal to 0. And it can only be equal to 0 when everything is 0. This type of proof is very useful when you're trying to prove things. If you're trying to prove that x has to be a certain number, you might be able to approach the conditions given in one way to show that it's greater than or equal to 0. And then some other condition might tell you it has to be less than or equal to 0. And then combining those, the only value you could take is 0. Right, so example, what real values is z satisfy this? Well, this is a sum of squares, right? And we want it to be less than or equal to 0, but we know sums of squares have to be more than or equal to 0. So this is only possible when it's equal to 0. And it means that a has to be 0, b minus 1 has to be 0, and this has to be 0, and we can solve based on that. Prove that if x is a positive real number, then 1 plus x is greater than or equal to 2. When does equality occur? So notice that 1 plus x, right, the left-hand side, you can actually write it like this. Square root of x minus 1 over square root of x, all squared. And if you expand that, you'll get a minus 2, so you add 2 to cancel it. Right, but this is equal to this. All right, and you could use this, right, because this is something that's a perfect square. It means that this is greater than or equal to 0. So the overall sum has to be greater than or equal to 0 plus 2, which is 2. So that you basically prove what you wanted to show. Note this is only true if x is positive, right? Because you can have square root of a negative number. So the proof doesn't hold there. Also, you have to be careful because, well, also note equality here is when x is 1, right? Because you need this thing to be 0 to have equality. This has to be 0, so square root of x has to be equal to 1 over square root of x. Yeah, so be careful, because if the question was something like, given that x is greater than or equal to 2, find the minimum value of x plus 1 over x. In that case, the answer wouldn't be 2. It would actually be something bigger, right? Because if the minimum value x could take is 2, it means that it cannot take the value 1. So it doesn't actually attain this value, right? In such a case, you would have to do something slightly different. All right, so these are some exercise questions you can try. Yeah, so you all should go through these. All right, we'll take a break and then start with means because this I want to explain properly, I guess. You wouldn't have seen those before. Does anybody have any questions so far?